Right.
Uh,
Yeah, and maybe if you have the recording from, did you upload it already to the Google Drive stack?
Yes.
Fantastic.
We
We are having troubles getting
a
the
connection.
Zoom. Okay, maybe
Yep.
I have an HDMI.
Pardon me. There is an HDMI here,
There is.
so I can swap to that. And see, I don't know why when did
Is this
I have to like undo this whole thing, I think. Um,
very good?
that's what I'll say.
Do I have any questions from students maybe before we go ahead and get started there? We'll just try and make sure all the dongles line up properly, but no questions. You guys are not awake yet, it looks like. Or we are awake, but we're not talking. Yeah, me too. There we go.
Hopefully this works. Um,
If it's doesn't work, then you can just send me the slides and use my computer.
computer having issues?
We're having issues with getting her screen to display on the thing. Just send me the
Can we try
slides.
with yours?
Yeah, just send me the slides.
They're just like the
Um,
I did not do any waiting for application. They're just the ones in here.
you should them join anyways.
Yeah.
Looking for them.
Yep.
That one that we think.
Sorry?
It's so hot in here.
It's really
It's not really. Try to do one. It's like colder outside.
Sure, go for it. Okay, some of the slides.
there.
Download those. All right. Close everything incriminating on my computer. No one gets to see my research. Thank you very much.
You'd get scooped if you're not careful.
That's very unlikely, but you know, you never know.
Someone's on the Zoom link.
Someone's
Really interesting.
fiending for my work.
Yeah, exactly.
Yeah.
Like that every time I do the LBNL, like keep your research safe. Like no one wants it. It's
Okay. Let me
yeah, I can
the
swap
computers.
And
Okay. Here we go.
okay. I'll play this first. I just think.
Oh, actually, you know what we can do is you can share your screen on the Zoom and I'll just project what you're sharing onto the screen.
Oh wait, is that going to be me? Oh no, I can. Okay, yes, you're right. Sharing is not turned on. I will send a request.
Wow. Why isn't the projector working? I picked the wrong one.
Yeah, I think it's my. I suspect it's my computer. So it should work here.
No, I just.
Okay.
Do you guys know about Berkeley time, what this is? It's a horrible scheme by Big Berkeley to make sure everything's late.
Hey, for in-person people, there is a Grace shoe, and they are wondering which door they can enter through for the in-person.
Okay, Grace, I assume on the one of these doors right here that are locked.
Oh. Okay, so like the ports on my computer are just straight up not working. Solid.
Okay, then I'll look around.
It's perfect.
So let me change this.
Okay. Cool. And then I can share the screen.
Fine.
Um, okay.
Great. Can all of us see the room properly? No else? Okay, so despite everything, today, Livia will be talking to us a little about fitting about bigger distributions. Livia is a graduate student here at UC Berkeley, and we're take it away. We have no time to waste.
Perfect. Okay, cool. I need to hang on one second. I don't really know if this is going to be possible to do. So I'll just try to point specifically at the, okay. Cool. Yeah, we could close those windows. Okay, cool. So we're going to do a little bit of a shorter talk today, and the coding is going to come next Monday because we're also going to do a research talk today by a professor at Berkeley. But we're going to get a little bit into some of the last Wednesday, you talked a bit about masses and momentum and kind of like looking at the remnants of a collision and understanding what happened during that event. And so we'll talk today a little bit about how people actually have used that to more recently make scientific discoveries. Specifically, we'll talk a little bit about the Higgs boson. Okay. Oop. I am massively overshooting. Perfect. Okay. We're going to skip through the review. I already talked a little bit about it. We've talked a lot about histograms and displaying data. And then you started talking a bit about, as I mentioned, physics and collisions and how you can use kind of fundamental conservations of energy and momentum, or fundamental conservations to understand what happened during a collision. And you did a bit of Python on analyzing data for that sort of thing. Okay. I guess, first of all, everyone was clear on the stuff talked about before. Sweet. Okay. We have no T's. Okay. So, how do we actually use this? You are all, of course, familiar, or likely familiar, and we've shown you pictures of these before, with some of the massive scale experimental like colliders that are built that are built across the world. And depending on how much you keep up with pop science, as well as kind of other scientific pieces, you'll have seen all sorts of kind of exciting discovery announcements come out about kind of different particles being detected, or kind of having restrictions placed on what these particles look like and what that means for a bigger understanding of physics. So particle physics is some of our kind of most basic physics. We have a lot of things that we know about the universe that we're searching for the reason for why they are true. And one of these is the Higgs boson. So we know things have mass. Experimental evidence shows this is true. We have tons of theories that show this is true. Things have different amounts of mass. They do different things. But we've had a problem about where that mass comes from. And this kind of graph that you see here was a very exciting graph that came out where that little bump tells us many things that support all of these understandings we have. And that little bump is the Higgs. So how do we do anything with that, and what does this mean? Okay, so we talked a little bit about kind of fundamental particles again on Wednesday. And the way that the Higgs fits into this is that the Higgs is a theoretical particle that gives leptons and quarks mass. So it is a theoretical particle that is going to allow us to build up mass across kind of different particles. And I recommend that you watch this video because it does a very nice analogy of kind of what the Higgs is. But the basic idea is there is this kind of field out there, the Higgs field, and interacting with it imparts mass. So some things interact with the Higgs, and some things don't. Photons don't interact, but leptons, quarks, etc. These things will interact with it, and this results in this observable kind of mass that has gravitational attraction that conveys so many of our kind of known quantities. And this builds up. So we said that the Higgs gives mass to quarks, and from there, this builds into the kind of particles that build kind of the rest of our world. So we have, protons and neutrons, a lot about. They build, all of our elements, which build our molecules, which build you, your chairs, everything around you. Indeed, guanine, DNA, that deer, and or you. So if the Higgs doesn't exist, we have a problem. So we spent a long time saying this particle exists. We don't know it yet. This is kind of the fun of like theory and research in general, is that there will be all sorts of things that are like well evidenced to be true. And we'll build all sorts of building blocks on them, and we'll still be searching for fundamental pieces. So for a long time, we said this is probably true. Now we need like a, pardon the language, smoking gun. So I pointed at that graph before that had that little bump in it, and I said, this is how we know about this Higgs boson. But how do we actually get there? So, fundamental process for doing an experiment. First of all, have an idea of kind of like, have a theory, right? In this case, the theory is this Higgs boson exists. But in other cases, it could be all sorts of other things. It could be, I'm searching for good examples, but it could be things about the way that forces interact with different like materials. If you're thinking about, theories in other fields, it could be about the way like plants grow, or the way that, plants like, chlorophyll, stuff like that. Basically, you need to have a fundamental prediction about how something interacts with the world, about how something works. And in the case of particle physics, to test it, you then undertake the also very simple step of building an accelerator, or getting time on an accelerator, which according to every particle physicist I know is tricky. So have a theory. For instance, there is a particle, Higgs boson. We have an idea about what it might look like in terms of, say, mass. And I now have time on a collider, an accelerator. With that, essentially the way that you're going to begin to test it is that you are going to have some sort of, you're going to look for a probability. So the universe is not kind of very static, and we'll get a little bit more into this in a second, but you're going to, okay, we'll get a little bit more into that in a second, actually. So, okay, we have a theory, we have time. We now need to test that. So the way that an accelerator works is you speed up particles. And again, you looked at this a bit on Wednesday when you did that math of two particles colliding and thinking about the masses. But you accelerate particles with some sort of known properties. And then you crash them into each other and you see kind of what you get out of that collision. And it can create a lot of things, and you kind of analyze all of this data about all the pieces that get spread out, right? So we already talked a little bit about the building blocks of neutrons and protons. So we know that even the kind of fundamental, as we think of fundamental particles, have lots of pieces in them. And so we are going to, out of this, so here's a little bit of a diagram of kind of two sort of fundamental particles, and within them, kind of fundamental building blocks. And as we do this collision, we are now going to get all sorts of interactions and all sorts of kind of different signals. And we're going to have to detect that debris. This is kind of a beautiful image of across experiments what that debris might look like. A little bit of an artistic rendition. But we are going to detect out all of those building blocks of our particles. And within this massive signal, we are going to be specifically searching for a signal at about the point that we predicted for, in this case, our Higgs boson, right? Different particles have different masses, have different properties. So we're going to be searching this large signal for a spike related to the species that we are interested in. Okay. Doing all right? Cool. Okay. So this is the kind of very basic idea of how these devices work. So essentially, you have we have kind of on the left and the right are two particles, and then we have a massive sensor panel that can collect, that can detect debris, it can detect angles, it can detect all sorts of things to tell us about what is coming out of this central collision. So, for instance, here we have a kind of, these are our before particles, and this is our kind of end signal. And this might be a no interaction situation. We kind of see that two things came out of our, collision. Probably means those two particles didn't really do anything special together. And this is a little bit of a dud. However, sometimes we get, more exciting things. We start seeing, more sensors light up. We start seeing more things coming out. And if we do this across many, many, many tests, then we can start outputting lots of data on what that debris looks like, what we input in, when there were interactions. Most specifically, what we care about here is we care about collisions where the two particles interacted and where we saw something kind of new and exciting. And so we're back to that spike where we see that essentially, so we see that, at a certain point in this kind of x-axis of mass, we're starting to see data. we're starting to see that something is coming out of that collision. It's not this kind of interactionless system. We're actually seeing something more interesting. And then we go back and we say, okay, we found a spike. Experiment tells us there's something there. We thought we would get X. Did we do that? We often talk about theory versus experiments, but you need both to be able to do anything. If you just do an experiment, without any idea of what's going to come out of it, you will probably not build it in the ideal way. And no one believes you if you just say, I have a theory and I've never tested it. Well, it depends. People love string theory, but it's tricky. So, okay. So now that we have those spikes, we have knowledge of what experiments gave us interactions. We now want to run that test back and see what was happening during that kind of collision. Okay. So now we're going to get a little bit into kind of some of the joy and wonkiness of actually doing experimental physics, because you would kind of hope that essentially the way that this would work is that you would kind of know mass, because there would be kind of one point where we would like see a thing, right? If like the particles have some sort of mass, then there will be a spike in our data when we fit that value. However, it's not exactly that simple. And this is where you're going to kind of use those histograms and that you kind of looked at before. So essentially, physics is often modeled as a resonating system. And we use that often to talk about probabilities. So there are certain probabilities where events are more likely and certain probabilities where events are less likely. In this case, we're thinking about that in terms of, So specifically, before we talked about that there were certain times where our particles wouldn't interact and there were certain times when they would. And when they don't interact, we think of that as a kind of non-resonance point, right? We mark that as a point on that graph where there's kind of no data. It's kind of zero on the y-axis. There's no kind of nice feature there. However, the resonance point is where the particles, or around the resonance point is where the particles begin to interact. And at the resonance, they're going to most strongly interact, giving us that kind of spike in data. So as particles are attracted to each other, we're going to start to see that debris come out, because when they kind of collide, they're going to create some sort of bound state. And that bound state will have some amount of time where it kind of survives, and then it will decay, right? You can imagine that if you have, two particles come together inside of that collider, there's all sorts of forces that can let them interact with each other. And they will have some sort of lifetime, right? You know about a little bit about like decay and lifetime and that sort of thing. And then when they decay, we get out that debris. And yeah. They do. So yeah. So that's where we see like lots of data. You send out lots of things. This is a kind of simplified picture.
Yeah, so the way to think about it is that what they do is they have a bunch of atoms going through this giant accelerator and like a 3 mile loop like that, like literally hundreds, thousands, millions of atoms in each other. But the size of the atoms relative to the size of the tube they're going through is like very, very small. So you won't really see pictures where a bunch of atoms are coming together at the same time in the same spot. Like that's really unlikely. It's sort of like if you had two people throwing a football from opposite sides of the football fields and like praying that they hit. Odds are they won't hit, and if they do hit, it must still be like maybe 2 or 3 at a time. Does that make sense?
It's a very, so the way these things are built is these are charged particles. And so the way that they can kind of interact with them with like electromagnetic fields. So these things often have these like extremely super cooled, extremely expensive magnets that can create a field to pull these particles. It's pretty cool. You need like very specific technology. Okay, cool. So we've accelerated these particles really, really fast. We've accelerated hundreds of particles, maybe more, and we now have an event where they are actually interacting with each other. And as they decay, they are going to decay in kind of every way they can. And we're going to get all sorts of signals off of our giant detector array as it sees all of this debris come off of our, crash. And specifically, if we look at many, many, many versions of these, as I said, these are kind of nothing happened data. But we're going to start to see these sorts of data points. We're going to see the sort of resonance feature where we see more debris when we are near that resonance peak where those particles are actually able to interact. And there are some very neat ways to describe that feature should look like. So this is a kind of theory that was put out that is used kind of across different particle physics work. But it can describe the shape of that feature that we saw on that graph based on the mass of the particles involved, as well as, or the mass of the resonance, as well as the decay of that resonance. So we talked a little bit about like the longer the particle it can live for longer or shorter before it decays. And these two features are going to allow us to describe what that resonance feature looks like. Which means that if we get one of these resonance features, we can back out what that resonance actually looked like, what that interaction looked like. Okay. Great. So now we're getting a little bit towards the code. So how are people doing? Sweet.
Number any questions?
Yeah.
What are some of the topics for the particle flash rate?
Very good question. I do not study particle physics. I know, yeah, I know particle physicists, but they're all looking for like neutrinos, so they don't use a collider.
So there's many different things you can use the collider for, many different types of particles. I am technically a particle physicist, even though I do quote nuclear physics.
Hey, Wyatt, can you speak a little bit louder?
study quarks or know about quarks, or like smaller objects that make up neutrons and protons. So nuclear physics is pretty much a big, like the Wild West in the sense that there's an equation that describes nuclear interactions and nuclear force, but it's not directly solvable with modern techniques that don't require big ass computers. So what that means is a lot of experiments in nuclear physics smash particles together and make a bunch of really complicated stuff that pops out of quarks. The stuff that pops out, they're not necessarily protons and neutrons, but there's other more exotic versions of these particles that are really, really short-lived. So as an exercise in making something that pops into existence for maybe 10 to 20 seconds, and then measure the products that comes out.
Can anyone ask Wyatt to speak louder? We can't really hear him online.
Gosh, that was a lot. I don't know if I repeat that. Essentially, you smash stuff together in smash nuclear stuff together. So like you smash atoms that contain protons and neutrons, or like gold atoms, or stuff like that. You smash them together to make a bunch of exotic particles called like mesons and baryons. And the goal basically of a lot of this type of physics is to figure out what the hell happened, because we don't have a good way of trying to guess the products and their masses and their decay widths based off of first principles. So there's a lot of data analysis and fitting in that region. Other avenues of particle physics that use particle colliders are stuff like, well, the discovery of the Higgs was, for example, one such thing. They smashed particles together to look for a bunch of events, which corresponded to a particle that they hoped to cure in our models, the model. So the discovery of the Higgs was sort of a validation of theory as a triumph in 10 years ago. Current research in particle physics, some people focus on neutrinos, which are these sort of particles that are weakly interacting, which appear everywhere, which come off from, say, solar objects, and they also appear in collisions. Yeah, in particle collider collisions, there's also attempts to describe other parts of the standard model, the big model of particle physics, via studying stuff like what's called the muons-2 experiments, where there's a prediction that says this one quantity is exactly 2, or really close to 2, and then an experiment came out about, I don't know how long ago, 5 or 6 years ago, that said actually it's really far from 2, you're wrong. And this caused drama. So there's a lot of experiments trying to validate or invalidate this previous result.
There's also stuff about like dark matter and is it possible to detect dark matter? And that's one where they do a lot of like, hey, here's a theory that says it might vaguely fall in this range, like here's what it might look like and here's how it might interact. And they do a lot of kind of narrowing space. They haven't found anything yet, but they are narrowing the range where it could exist.
Yeah, dark matter is a different can of worms, because there are dark matter experiments that both use particle colliders and do not use particle colliders, because, well, ask me later. Another question.
They just said that they missed all of it online.
10 out of 10. Okay.
But they heard it. Sorry.
It's just my voice. I'm just not good at projecting.
Yeah.
You smash stuff together, cool stuff comes out. Physicists like to argue about the results. A lot of it's important, a lot of it's really not important. What is and what isn't important depends on who you're asking. It gets very dramatic. Another question, yeah. Oh, this distribution right here? So I wouldn't really call this a derivation of a distribution, more of as an acceptable fit to a distribution. Maybe if I go back once, yeah,
I don't really think there's much more in here.
Yeah, so there's no like big physics TM reason as to why this particular equation fits data like the one down here. So this is the Higgs, as Livia mentioned many times. It's just that the curve, this little red curve, if you zoom in really closely on that, that's this exact function, and it works well for resonances for particles that appear in particle colliders when there's not a lot of other stuff going on near them. You can have particles that are really close together in mass, for example, and if they were close together in mass, then you would see a lot of bumps like next to each other, which is not well described by this type of model. This is sort of like
a dream case where you have one single particle appearing at one single energy region, and it decays nicely, and it follows this distribution where we're sort of scanning in energy. So the x-axis is energy, m is the mass of the particle that we're making, and then this gamma is how long it lives. It's its lifetime essentially, or it's related to its lifetime. It's called the decay width. It's called a Bright-Wigner. You can Google it for more historical information, but it's not really it's a fit. It's a function that you fit with, not a function that you should that should survive in 50 years as being the answer to everything, if that makes sense. Other cool questions about physics? Online or in person? Great. I'll back off then.
No, it's good to have an actual particle physicist. Okay. Okay, so now that we have a kind of idea of how we do these experiments and what you can get out of them, and an idea of kind of how you might fit them, or at least a good first thing that you should try. Here are some kind of plots that match this fit. So these aren't actual data. These are just, we gave it, an M and a gamma, and here we have kind of E versus probability, and outputted these lines. So as we start to understand kind of what these fits and what the data that we're trying to fit should look like, first question is, does anyone have a guess as to what mass we gave these fits? Exactly. Yeah, so that's our resonance, right? We said that at a certain mass, we would see kind of the highest spike in probability. It's about 2.5. You can kind of look at this and pretty can see from this that probability is maximized for that specific M. So then the question becomes, what do we think that kind of decay term does to these distributions? So here we have kind of 3 different distributions. They're all at the same point in M, right? But they all have different gammas. So we're saying that there's a resonance feature at this specific mass, but it decays on different kind of time scales. This interaction decays. What do we think the ordering is? Do we think that we'll just do a poll of hands here. I can probably guess that it either goes 1, 2, 3 or 3, 2, 1. So do we think that the sharpest spike is found with particles or with interactions that decay faster? Or do we think it's found with interactions that decay slower? Do we think that that kind of red curve corresponds to gamma equals 1? Raise your hand. Do we think it corresponds to a slower decay of gamma equals 3? Okay. We had very little input. First one.
Raise your hand if you think that n equals 1. Raise it high.
Awesome.
Raise your hand if you think n equals 2.
Gamma equals 3.
Raise your hand if you think n equals 3.
Cool.
Okay. So we got.
We didn't have. You picked 1 and 3.
So you raised your hand twice. Yeah.
You hedged your bets. Not the best way to run the experiment, but fair enough. Yeah. So, okay. Perfect. Okay, so if we take a look at this, we said most people thought that a shorter decay length would give us a bigger peak, and that would be correct. So the faster it decays, the faster it decays, the kind of, you can see here that we have, two versions of gamma.
Wait, sorry, did you say we picked n equals 1?
Yes. Yeah, exactly. And we can kind of see here, if we're just looking at the math, that the numerator goes with gamma and the denominator has a term of gamma squared. So the bigger our gamma gets, the kind of smaller our peak will be. Okay. So you have a little bit of a sense. Maybe now if we looked at this guy again, you could tell me a little bit of stuff about what you think is happening here in terms of, M and gamma. You could give me a guess. But we're going to need to do a better job, because putting a guess of, I vaguely ballparked it as, this M and this gamma is not going to cut it in a scientific paper. You're going to need to fit this data. You're going to need to kind of attempt to actually take data points and apply a curve to this data based on this equation, and pull out that M, pull out that gamma, and you're also going to need to tell people about how good that fit actually is. So those are the key things. When you do an experiment and you look at that data and you say, I think there's something there, the next step is, and this is kind of theory versus experiment versus now we're getting some more kind of light computational work, which is the third axis, the third secret axis to research sometimes, where you need to actually process this data. So, how much time do we have? Guest lectures at 11?
Yeah, another 10 minutes or so.
Okay, sweet. So, to kind of start this out, okay, so we'll go back to this for a second, actually. We have this data, and we can immediately tell that one of these fits is better than the others, right? That green fit by eye looks better. Kind of, these are our little data points, circle with an error bar. And we can immediately tell that that green curve is a better fit than, say, that blue or red curve. And you could imagine that the way that we can kind of do this is we could draw a bunch of curves and we could see which one is the best fit. And that is what, when you actually do this work on a computer, that's what your computer is going to do, is it's going to try a bunch of things and it's going to have a systematic way to decide whether a fit is better or worse than another fit. And then it's going to keep trying until it gets kind of whatever it thinks is the best fit. Yeah. Totally. In this case, we probably won't have that. But if you ever kind of do these sorts of fits, that is a problem that you will sometimes have, where a computer will find a good enough fit and it won't kind of find the best fit. And when you get into more computational physics, that is a problem that people think about. So we said that essentially the way to fit this is try a bunch of things and have a way to determine which out of these is the best fit. So let's make it systematic. Not exactly, but a bit ago we talked a little bit. So this is an expression for how good of a fit you have between a data point and kind of where a fit tells you that data point should be. So essentially what we're doing here is that we have actual data. We have, I should not point at that because no one online could see that really.
Yeah, it's just referring to it verbally.
Yeah. So we have yi here, which is our actual data. That is kind of the measure value that we got out of our experiment. And then we have pi of m and gamma, which is our kind of fit. That's our, we drew this distribution. That's where the distribution that's where the distribution data point lies at. And then we have this kind of standard deviation, which is essentially, there's a little bit of kind of, if we're doing some, more sort of binning stuff where we have a kind of distribution on where that data point might lie on the x-axis, then we account for that. But essentially the idea here is, this might look familiar to you. We have a point minus another point squared. We're looking at distances. We're looking at how far away from the actual value our predicted value is. And then we are summing that up for all of our data points. So we're seeing if overall our fit lies along the line, if it on average lies decently along our data, but for some data points it's off, or if we output a really, really big value, then our fit just completely doesn't match the data, and we need to try again. And this is actually how this is how when you kind of write a program, it will look at this data. And our goal is to minimize this function. Ideally, you hit 0. You've done a perfect fit. You're not going to hit 0, but you can get close. And as is pointed out here, we can now use this and apply it to this data set and this fitting to determine that we are not doing a great job. And we can probably do better. Yeah. In this case, the standard deviation is, there is some kind of, here we've, yeah, so we have, yeah, so essentially.
So yeah, sigma I standard deviation of the I energy bin. So what's been done is like in the previous exercise where you guys like had a bunch of data that's close together, like combined into a bin. So this set of this sigma I is like the spread of all the energies that are close together in one energy. So it's an estimate for the error of the data point of that energy bin. So there's a different one in the next slide. There's a different one. It's the size of the vertical bars here is actually but am I too quiet? The X and Y axes?
Here we're looking at, here we are looking at our mass, and then we're looking at that probability function. So, was there another question? Okay. Okay. So, now, essentially we before looked at that kind of fit function, or the actual data, and now we're looking at how our fits are. So essentially what we're doing here is we're trying to look at, this graph is a little bit, essentially we are trying to look here at what choice of parameters is actually going to give us kind of that smallest distance between our fit and the actual data. So this graph has its mass versus kind of the deviation from our data. And each of those kind of curves corresponds to a different gamma. And any kind of value above 0, so if we look at like a point here, if we look at a point, say along the x-axis is at like 4, and then we look at that red line, that means that we're looking at, we've chosen a fit that is mass 4, gamma 0.5. And then we can track it up and say, okay, we have a big deviation, right? That means we didn't fit well. And our goal is to minimize. So we're looking for the values that minimize that y-axis where we go to 0. And so we determine from this, when we were fitting that kind of data set that we made, that point at about 3 for gamma equals 0.5 is our minimum. So essentially, we just test a bunch of fits. We give it a lot of different values, and then we use this probability, or we use this function to output which values match our data the best. And that tells us about that interaction, right? What was the mass and what was that decay time? And in general, we're going to go to coding because this would take a really long time to do by hand. And I think that I don't know if I start going into coding right now, if that is going to stick for
So we are
7 minutes. So
we will
maybe.
have a guest speaker, Victoria Shu, will talk to us about her research.
Yep.
So if
This
you are
will
bored in the
be-
next 5-10 minutes, what you can do is you can take out your laptop and start messing with this code with the notebooks that I haven't yet uploaded to Google Drive, so I'll do that in a moment.
Oops. Okay. So if you want to take a look, it'll go into this kind of fitting. But there will also be time to do that on Monday.
Yes.
So you do not need to feel very rushed in that.
Yeah, so I propose we take a bathroom break and then come back and you can amuse yourself with the code for a few minutes while we await our speaker. There will be donuts, there are donuts in person here in the room again. Hopefully you're not sick of them from last time.
Today,
We don't have the stuff.
today is project 4. I don't think it's uploaded just yet. I can.
Project 5.
Yeah, I'll upload the slides in a moment and then you're welcome to do it.
Am I able to upload them or something?
Yeah, so we can shortly.
Hi, everyone.
Next method of nukes, they're going to use antiprotons to make a nuke. Is that true?
Sorry, who's going to do what with
They're gonna
antiprotons?
They're going to make nukes out of antiprotons.
Probably not. Probably not true. Regular nuclear weaponry uses protons, and antiprotons wouldn't provide anything more interesting because it's just a proton but anti. Like you wouldn't get more energy out of basically an anti-nuke if that would make sense.
No, using antiprotons.
Yeah, well, so there's nothing really special about antimatter versus regular matter. It's just
Isn't it that when they will like annihilate each other and release a ton of energy, according to C squared, whatever that one is.
you're talking about, sorry, Q squared. Yeah, I mean,
I learned that somewhere.
the cost of producing antimatter far outweighs the energy you would get out of the antimatter
Then why do we make it antimatter?
for physics, for research alone. Yes, it's not really going to help us in terms of technology.
And wait, is it true that like the universe has antimatter a lot? Is that true?
No, the opposite is true. There is basically no antimatter.
Wait, then how is it like positive?
How is what
There's
positive?
like positive matter then. How's that even possible?
This is called the baryon number asymmetry. It's a big question in physics, actually. It's a question about cosmology. So at some point in the early universe, more regular matter was made than antimatter, and we are consequences of that. Because if the total amount of matter and antimatter was the same at the start of the universe, then maybe I don't know what would happen, but I certainly wouldn't be here to talk about it.
Yeah.
Yeah. Yeah, but go get a donut. Don't mhm. Livia, this was project number 4 or 5, 4, right? So I will take these and download them and add them to the drive.
I'm gonna use the restroom.
still a full way to do
Yeah,
it.
we're gonna talk about
Right.
gravitational waves.
All right.
Okay,
Vicky,
so
you wanna grab your donut before somebody steals them?
Ooh, I would totally grab one of my donuts. All right, let me just like, what is happening here?
I think
Okay.
you said glaze.
Ooh, yes, that would be awesome. Okay, great. Let me just like, let me just do this. All right.
Okay, everybody, and we're unmuted online?
I think we're unmuted. I don't know if we can tell whether people can hear us.
Yes, we can hear you online.
Okay, awesome,
Okay,
great.
great.
Okay, so we have a special guest today, which means that we're gonna grab all our devices and put them away. I don't wanna see any laptops, phones, or anything, or tablets of any kind. So it's a real pleasure to introduce Professor Chu, who's gonna be telling us about gravitational waves. Vicky Chu, she's one of our most recent additions to the department. She joined us last year, and it's been a real pleasure getting to know her. She brings a whole line of research, which is really exciting. But before I tell you about her research and my little bit of take on it, I'll tell you a little bit about her bio. She's a local Bay Area native, just like you all. So, just keep that in mind. She did her undergrad in UC Santa Barbara, then came back here to do her PhD here in the department. She then went to MIT as a postdoc for a relatively short period of time. So if you don't know what a postdoc is, well, actually, some postdocs. Postdocing in some place, at least for me, it was like the best period of life academically. It's like you just get to do research and it's really great. You don't have to worry about anything else except the next stage of life, right? And so, that can go relatively short or long, but she was there for a short period of time, and then she came here and just joined our department where she's now a professor. So what she's going to tell us about is gravitational waves, but in particular, her research is really fascinating because she basically uses the quantum world to make detections of gravitational waves. If you haven't heard about gravitational waves, I'm sure she's going to tell you all about it. But when I first learned about gravitational wave detections and the kinds of experiments that she works in, I was a grad student at the time. This was back in 2010 or something, which was, the experiments were still being built. And that to me sounded like science fiction. I was like, there's no way these people are ever going to detect these gravitational waves. It is completely impossible. And about 7 years later, they sure enough detected it, and immediately they were given out Nobel Prizes because it is such a tremendous achievement, scientific achievement. We're really one of the greatest scientific achievements over the last 100 years. And it's really opening up a large set of new physics and science that I think it's really exciting and that maybe all of you want to explore in the future. So it's a real pleasure having Vicky join us today. Why don't we give her a round of applause and
Thank you. Yeah, thanks all for being here, and yeah, thanks for bearing with me for like almost the next hour. So let's keep this interactive. So just like if you have questions, you can say them out loud. You can raise your hand as we go. That's all good. I'll just start with a little bit of like who I am. So like Rahul said, I'm from San Jose originally, kind of like East Side San Jose. So that's sort of where I grew up. I kind of took my first physics class in my junior year of high school. Are you all high schoolers? Right? Okay. Yeah. So if you're a junior, that's when I took my first physics class. I thought it was cool. I took AP physics in my senior year. And then, yeah, I went to UC Santa Barbara. I wasn't sure I was going to do physics, but then kind of that's what I thought was cool. So then I stuck it out for majoring in physics at UCSB. For grad school, I came back to here to do my PhD in this department, actually in atomic physics. And after that, I went to MIT for my postdoc. This last point is outdated, but yeah, it's kind of cool that, as things go, like I've always worked on kind of the technology side with lasers, and that brought me to atomic physics. quantum physics, and now kind of into this new type of astronomy with gravitational waves. It's cool that you can work on lasers and end up working in astronomy with that kind of a background. Okay, about me, just a little bit outside work. I'm not a terribly interesting person. I just kind of walk around, eat food, hang out with friends. I like being outside. Yeah, so I don't know if you meet a lot of scientists, but we're regular people too. More about me at work. So I'm now here as a professor. I just started in January. Before I was a postdoc at MIT. And that's where I really got involved in this LIGO collaboration. That's the Laser Interferometer Gravitational Wave Observatory. These are two NSF-funded facilities. And my main focus is on, one way you could say it, is squeezing every little bit of performance possible out of the gigantic facilities that we've built. And so that's what I'll talk about today. And in particular, the reason that that matters and the reason I use the word squeezing is because one of the biggest problems for our experiment is actually essentially the fact that quantum mechanics is real and that it exists. So quantum mechanics means that there's this sort of quantum noise, it's pervasive, it's everywhere in space. And we'll talk a bit about that. But what it amounts to is like, if you took a box anywhere in the universe, like literally anywhere, and there were no lights on inside of your box, you would still measure that there was noise in the light field, which is crazy. You could take a dark box. There's absolutely no light. There's no anything. It doesn't matter what frequency band you measure it at. Doesn't matter if you're measuring like Wi-Fi to 5 gigahertz. It doesn't matter if you're measuring a visible color. It doesn't matter what frequency of light you're measuring. You will always find there's some noise on any detector in any dark box in the universe. That's because photons are inherently particles, and they can essentially pop in and out of existence anywhere in the universe. And for our detectors, I'll show you a bit more, but that is a huge problem that they randomly pop in and out of existence. And so that's the quantum noise problem. And so what we do is squeeze the quantum noise to increase our sensitivity. Yes.
But what if there's like, like in like a vacuum environment?
Exactly.
Then does photon randomly appear still?
It still does randomly appear. And
And why?
yes.
That's very, very weird, honestly.
It is weird. So some people, once you're old, you might call this job security. The fact that quantum mechanics works on particles, there's the Heisenberg uncertainty principle, and we'll talk about that. And what that means is you can't know exactly when and where a random fluctuation in the light field will be. And that essentially guarantees that there's always noise. And I'll tell you about gravitational waves, how we use laser light to detect gravitational waves, and why these random fluctuations exist, and why they're a problem, and why we have to engineer them so they're less problematic for us. But exactly like your intuition, it is super weird. And this is the weirdness of quantum mechanics and just generally quantum engineering. You can try to use this to your advantage, but in our case, with astronomy, we're really plagued by it, and so we have to reduce it. Yeah.
What do you mean by speeds, like the data?
We will talk about that. We will get there. We will get there. Thank you. You guys are very smart high schoolers. I'm very impressed. We'll get there. First, though, let's talk a little bit about astronomy. So to talk about astronomy, and specifically to talk about like gravitational wave astronomy, this is a totally different type of astronomy. We'll get there, but just talk about gravity a little bit. People in everyday life, what you know about gravity is that you drop something and it falls down, right? That's the obvious form of gravity. What is the less obvious form of gravity? The less obvious form is what we might call general relativity. And one question that's kind of at the crux of general relativity is that imagine between me and you, there's a really heavy object. How does light travel between you and I if there's a super heavy object here in the middle, right? So people say, space-time tells matter how to move, right? You drop an apple, it falls down. Space-time tells matter how to fall. But matter also in turn tells space-time how to curve. And that redefines what falling means. So yeah, if there's a big heavy object between me and you, how is light going to travel?
Don't know, like curve.
Exactly,
Yeah.
right? It's not going to take a straight path anymore. And that's kind of the crux of general relativity in some obvious sense. But you would never think of this problem unless you were looking at the stars, right? Because for kind of day-to-day objects, like I've never met, anything on Earth that is so heavy that really the light is bent around and lensed by its gravity, right? You really notice this on universe type scales. And that gives you a sense that gravity, it's, in some sense, it governs everything we do every day because you're always walking, but it's also very weakly interacting because it takes starlight to make moves of light. Yeah.
So is that why when we do gravitational lensing, like the body we use to distort the light,
Yes.
they're very large clusters of galaxies?
Yes.
Or stuff.
Exactly. Yeah. Like, for example, a human would not be enough to gravitationally lens, your arm around them such that I see this, smeared out image of your arm, right? Exactly. Yeah.
Should we be scared of black holes?
That is a great question.
Because I think you're like, it's not even a neutron star. It's like infinitely small, right?
It's not infinitely small. It's small, but not infinitely small.
How small?
How small depends on how heavy it is. Yes. Wow, you guys are like extra smart high schoolers. Yes, exactly. So let's talk a little bit about gravitational waves. Oh, before I talk about gravitational waves, this is the kind of image I want you guys to have in mind, right? Like heavy objects, they deform space-time. That changes both like what's happening on this clock, that's space-time, and it changes how light moves around it as well. So then what are gravitational waves? Gravitational waves are exactly when you see these two bodies and you see them orbiting each other, you can imagine there are ripples being radiated out into space, right? And that's what gravitational waves are. If something like that happens, there's this event happening at a super exaggerated scale, you'd see something like this on Earth. You would see that if you had two directions like this, they would kind of dance around like this because gravitational waves are coming through Earth. I can play that video again just to give you a sense of like what it looks like. If you have gravitational waves being radiated by two objects as they're kind of inspiraling and catching each other, this is kind of what you would see on Earth. Obviously, you don't see this because the Earth would like actually explode if we actually saw this, right? But that's how you can kind of see the signal from these gravitational waves passing by. And what you see then is that if we had a distance L and we had two distances L, they would kind of do this sort of dance, right? Like one gets longer as the other gets shorter and vice versa. That we call a strain. And specifically the strain is delta L, the change in length compared to the baseline of L. So we call that quantity strain. And something to notice here, sorry, it's a little cut off, the strain is about 10 to the minus 18 meters over a baseline length of 2.5 miles. That's very small. And I'll show you in a bit, a little bit more how small it is. But like this signal of about 10 to the minus 18 meters, that's what we can see from the heaviest objects in the universe, right? It takes really, really heavy, huge things to even produce a signal we can barely measure on Earth because gravity is so weak. Yeah. Yes, we will talk about that. Okay, we can skip through some of this to get to like the more interesting questions you guys are asking. I'll just say a little bit about these things, just so you have some context about what we'll actually see with gravitational wave astronomy. What it takes to make a signal that's actually like visible is, for example, neutron stars and black holes. So neutron stars are basically we can go here. This is just a cool like animation of what happens to stars when they die. They generally explode. And what it takes to generate gravitational waves is huge changing matter density. That's essentially what it takes to generate these ripples. And so that's just a cool animation of stars dying. If you look at the life cycle of kind of stars, right? The types of things that we're seeing that are heavy enough to generate gravitational waves are when you have a really big star. For example, you start out with a cloud of dust. This cloud of dust has pieces that implode into stars and form stars. If a big cloud of dust forms a pretty large star, that can lead to the explosion you just saw, to supernovas that explode. And if it's sufficiently big, it implodes into a black hole. If it's pretty small, like on the order of the like a sun to a few suns heavy, then it'll collapse into a neutron star. And then so what you have in the end are just these sort of dark objects. Again, these are like black holes. They don't inherently emit light, right? They're dark. And they're just kind of like hanging out in the universe, just zipping around in the universe. Let's see, will this image ever evolve? They are so heavy that they will attract things if they get close enough to other stuff. So like that's how these two black holes, for example, can find each other. Eventually they can randomly, chaotically zip past one another and they can catch each other gravitationally and then in-spiral into a final object. And what causes this two-body system to lose energy such that they actually in-spiral? It's because they're radiating gravitational waves. So they're losing energy as they're in-spiraling, and that causes them to form a final object. Yeah.
I see. When you say that black holes or the merging of black holes is probably strong enough to create gravitational waves, there's many different types of black holes with different masses.
Yes.
So is it usually stellar mass black holes? Or
So these ones we see are stellar mass black holes. Yeah. And we'll get into more of that whole spectrum of things. Yeah.
And do all binary black holes merge, or just a chance?
All binary black holes, if they are really in a binary system, will eventually merge.
How long does it take for this to work?
It depends a lot on their mass. They can, if they're kind of, so this was the first kind of event that we've detected for black hole astronomy, for a binary black hole system that catches each other, in spirals, and merges. Then you can see kind of like what they do to the space-time around it, right? You can tell that if you considered a flat ruler on that grid, that ruler is getting modulated, right, by these oscillations as these two objects merge and they radiate the energy away to lose energy to become a final object. And what we measure in our detectors is exactly that delta L over that baseline L. And so for this object, I'm sorry, it's cut off here, but what you're really looking at is two 30 solar mass black holes. So two black holes are 30 times the mass of the sun. They actually, we're seeing this very kind of, slowly. This actually happened in about a quarter of a second. That's how fast these objects collapse. And they're moving at like almost half the speed of light when they do this. So this is like a totally crazy astrophysical event that exactly becomes a barely measurable signal. So this was the first detection of a direct detection of black holes merging. And so another thing, like I said, is interesting to look at. Maybe this is especially interesting for folks like rules to think about, is what happens if you're not catching the merger of black holes, but you're catching the merger of neutron stars, right? Neutron stars are that smaller byproduct of stellar remnants that can collide. And again, like neutron stars are kind of crazy. They're just like neutrons and then gravity pulling them inward. And they could be like perfect spheres, and they're about like the mass of 1.5 suns in kind of the distance between us and San Francisco. That's how dense it is. So if you had a spoonful, it would probably weigh as much as a mountain. So this is like a crazy object. And you can see these objects, and like this will kind of give you an interesting sense of why gravitational wave as a type of astronomy is awesome. So neutron stars will kind of in-spiral and merge as they come together, and then they start losing energy from gravitational waves. Because they're neutrons, you have this like crazy fusion process that essentially starts in once the stars merge, because you have all this high density nuclear matter colliding. That emits light. Once it emits light, then we can do a bridge between gravitational waves watching the motions of dark objects and optical telescopes on the ground. And so, the neutron stars explode and we can eventually actually see the light. And this was a really cool detection that we were able to do in 2017. Oh, okay. So this will play actually what it would sound like to hear neutron star mergers. And then that is actually like a gamma ray satellite in space that can detect the gamma ray burst from this event. And this is super cool because once you can detect all of this together, then you can do triangulation, right? Like the two LIGO detectors can be like, I heard one here and I heard one here, and the telescope can be like, yeah, I saw it over there. And then you can actually say like, which constellation and where in the sky did this thing explode? And the crazy part about that is that like, if you just think about what's happening, like, gamma ray satellites are looking at not visible light, right? But most of what you think of when you think of telescopes, you think of like a dome that opens at nighttime, right? Like we don't have that problem. We don't have to wait until nighttime. We don't have to worry about if it's cloudy in the sky because we're measuring space-time distortions, and that's happening everywhere, right? So once the telescopes close their domes, once it's become nighttime and they can open up, they can actually see the blinking here of this transient event. And so this can really make gravitational waves a cool new messenger of transient high energy astrophysics, which is super cool. And then they can follow it up. So we see gravitational waves, like once then the light can actually leave this thing exactly 2 seconds later, then the gamma rays detect it here. But then we can see it like everywhere, right? We can see it at all the different wavelengths of light. We can see gamma rays, X-rays. We can see it in the ultraviolet. That's kind of the same wavelengths that give you sunburns. We can see it in optical, like all the different colors of this nuclear reaction glow differently. And so we trace this event all the way through out until like radio bursts are still happening a month later. And so this is like a really exciting thing for astrophysics. And something we can learn, for example, is that a lot of the elements that like are heavier elements in our universe, the way they're produced, one mechanism is neutron star mergers, is how you get things like gold naturally in the universe, which is pretty cool. Okay, so now we'll go to the question of how small is really 10 to the minus 18? This is an atom. If you were to zoom all the way in on the atom into a proton, what we were looking at is like this. It's a fractional change in the radius of a proton. That's how small 10 to the minus 18 is. And we're looking at a change like this over a baseline of like 2.5 miles. So 2.5 miles is like, it's a small service road. So like if you're like me and you leave your laptop charger at one side of the facility, it's going to take you 15 minutes to drive there and drive back. And we're looking at this level of change, fractional compared to an atom. So this is a very, very small thing. It's less than 0.1%, the radius of a proton. And so at this scale, people typically think of quantum mechanics as like, whatever, that's a thing that happens in a vacuum. That's a thing that happens at such a small scale that nothing matters. But at the scale of protons and subatomic distances, it's like a gigantic effect. And so this is why we really have to understand quantum noise and know how to deal with it. And so how do we actually measure something like this? We do what's called interferometry, laser interferometry, and I'll get to showing you photos of it in a second. But this animation can just sort of walk us a little bit through. The main laser goes to two things. As the two arms move exactly like that, that's what produces a signal like this. It effectively changes the power. So let me just play that again. You have laser light that comes in, splits two arms. The waves interfere and you change the power at the output photodetector, right? So what have we done? We've turned this length change into the power at a photodetector, and that's exactly this signal right here. Okay, we won't look at all of this, but you can kind of see from here, right? We're changing the length by that much, but the real thing that we're really measuring is the power at a photodetector. That amounts to like, you can change the brightness in a room. That's effectively what we're measuring at the end of the day in our giant facilities. And if you just think about like, how good can that power measurement even be? If these two waves are not matched to within a quarter of a wavelength, if they change by a quarter of a wavelength, and we use laser light at 1 micron is like 1% the width of your hair, roughly, something like that. So if you change by like 0.5% the width of your hair, the power we measure at the output photodetector goes from completely bright to totally dark. It's like in a room, if you turn the lights all the way on to all the way off. For us, we've transduced this, fraction of a hair measurement into detecting whether the lights are totally on or totally dark. That's how you make precision measurements, right? You encode variables and more bigger measurable things. You have physical lever arms to magnify your measurements into different quantities. Yeah. Yes. Oh, good. Okay. So this is a simplified photo, right? So what we're detecting in the end is the amount of, we're measuring the power here, like the brightness, but what that really is the number of photons per second, right? And that comes into part of this of how can we get the maximum amount of signal photons per second. And so, okay, let me go through a little bit of a detector overview. This is what I would normally do. If you go to any of the LIGO facilities, I totally welcome you to go on the second Saturdays for observatory tours. So this is a detector overview. You park your car over here. The office is over here. And we saw that laser light goes into a beam splitter, and then it goes down two of these 2.5-meter arms. That's these arms over here. This is the drone photo, and you have the final photo detector roughly here. So this is how our giant facilities map into a laser interferometer. If you go into the instrument halls, you'll see all this huge equipment. The size of a person is here, right? And what all this big equipment is, like these giant steel tubes, these are giant vacuum chambers that we've evacuated such that a random particle in there is not going to hit another random particle for about a kilometer. It's a pressure about 10 to the minus 9, 10 to the minus 10 torr. And this is one of maybe the second largest vacuum system on Earth that we operate for LIGO. And that's because if we have the lasers traveling that distance, they can't be hitting random air particles that come by, right? So we need a giant space with no particles. That's why we have giant vacuum chambers to contain the laser beams across the entire facility. And then you see these big structures and like these big things, right? So what's in those is a very, very elaborate seismic isolation system. And that just makes sure that if somebody like walks by one of your mirrors, they're not moving the mirror. So we get a lot of vibration isolation by suspending pendulums. So all of our optics you can see here, our core optics are suspended on quadruple pendulum stages from actively controlled in vacuum optical isolation tables. And this is just to show like, it's the simple concept of, right, we just had a mirror. Like we were just sending laser at a mirror and it's bouncing back. That's like all we're really doing, right? But anything can move this mirror. We're looking for an extremely small movement of the mirror, which like if a person walks by, that's enough. If a fan blows on it wrong, that's enough, right? So we have to isolate from all of that, which is why we have this very complicated quadruple pendulum system. The mirror part here is just the bottom stage of the pendulum. You can see this is the mirror compared to one of our detector engineers on site here. And so these optics are incredibly well contamination controlled in the sense that here what you're seeing is that as we're servicing the cage that contains the optics, we have this layer to make sure that random dust doesn't fall onto it, and we peel off this polymer layer when we're done. And so what it amounts to is we have very, very, very high quality mirrors, and they're isolated really well from seismic noise. And there's not just one, of course, there's two LIGO detectors, one that's in kind of an hour north of it's Louisiana, New Orleans, and another one that's about 3 hours east of Seattle. So these have about a 10 millisecond light and gravitational wave travel time between the two opposite sides of the US. But there's also detectors all around the world. So we have an international gravitational wave network, right, for triangulation. So there's the two LIGO facilities in the US. There's the Kagura detector that's in the bottom of a mine in northern Japan. There's the Virgo detector, it's about an hour north of Pisa. And LIGO India is now starting to be commissioned as well, which is pretty cool. And so this is just another drone video of the facility, just so you can see kind of the scale. Again, these are the big vacuum chambers that come out of it. This is a very elaborate video. We're not going to watch all of it, but just to show you the concept. This is the Louisiana detector. It's kind of in a marsh. They're actually logging right now. But I just want to show you what the inside of these kind of look like. Yeah, here. So it'll go inside the beam tubes. You see there's this huge vacuum system that's protected with this steel cage with this beam structure. And so the laser runs inside of this vacuum system. Yeah, that's how it goes to 2.5 kilometers, or the 4 kilometers, 2.5 miles in that vacuum system. This is just like if you're walking around lab, as I would call it, this is what you would see, these really elaborate seismic isolation structures. And yeah, so that's what we have on site. And so again, what do you kind of hear if you were to listen to these signals? They're filtering, it's a little chirp at the end. That's like in real time how fast these like transient volatile signals come by our detector. And then the next question is like, okay, cool, but how do we know what just showed up if we all just heard like this little like, or like this little like chirp thing, right? And so here, the signal that we see is a function of, for example, how far away the source is. So you can look at this 800 megaparsec. Just for context, parsec in space is about 3 light years, 1 megaparsec is about, it's 1.5 times the distance between us and Andromeda. Because gravitational waves are so weak, they can see much farther into the universe than most telescopes because they don't have the dust problem. Most telescopes have a hard time seeing way beyond the confines of kind of the Milky Way because there's so much interstellar dust. And so with gravitational waves, we can trivially see at today kind of like out to 11 or 12 billion light years away. That's not that hard for us anymore today in gravitational waves. Yeah.
What about Andromeda?
Andromeda is very close. So yeah, Andromeda is actually about like 0.8 megaparsecs away from us. So compared to 800, it's very close. Andromeda is like our nearest galaxy. It's quite close. So you can see here, the waves will get louder as the distance and the frequency will change with the mass. So you can look at that here, right? We're changing the distance up at the top. That makes the signals that we see from the source bigger. If we change the mass, that changes the frequency at which they inspiral, so we'll see that change. And the detector is not equally sensitive at all frequencies, so that will change there. And we can do this fast template matching, and then basically I'll get a notification, I'll get a text on my phone in like 5 minutes with exactly what we saw in the error bars, because we can do this kind of fast parameter estimation. And that's because most of the signals we see today are like, signals that we kind of know what they look like. They look like standard black holes that are around the mass of our sun, stellar mass. But there's all sorts of stuff you can see. There's all sorts of exotic stuff. People are really hoping to one day see black holes that were emitted or gravitational waves emitted from before the cosmic microwave background was emitted, which would be the most like amazing thing in gravitational waves. Yeah.
Something we're just starting about fish. So like,
Yes.
the previous plot they were showing is a really nice example of
Oh yeah.
you have a functional form, different parameters, you're trying to adjust the data using exactly the ideas that you guys were talking about.
Yeah, yeah, and there's a lot of fitting in LIGO. There's fitting, there's fast fitting, there's elaborate fitting, but a lot of it is really this sort of fitting is how we can get the fastest answer. And then we spend time to refine it after that. But we do fast fitting because, if you see a thing, you want to know like how big was this black hole and like where did it come from? But the even more important thing is for the multi-messenger astrophysics. We need to fit it within like moments if we want to tell telescopes like, hey, look over there, there's something blinking right now, right? Like that has to be fast. And then we send out a NASA alert and then we alert all the telescopes of where to point. And then it goes from there. So there's a lot of like, there's fitting, which is good, like careful fitting, but there's also like, what is it right now though? And that's this sort of fitting. Okay, and so when we look kind of at the last kind of 3 observing runs and we see like, okay, what did we see with gravitational waves, right? So all the things that are here that are in this bottom, like this red and this yellow, that's all the neutron stars and the black holes that we've inferred from like normal optical telescopes, things getting lensed around small things, binary systems, stuff around them. So we've only kind of known, without gravitational wave detectors, we only knew that these guys existed. But with gravitational wave detectors, we're starting to see like you'll see a thing merge with a thing and it become the final product of another thing. We're starting to see like there's actually tons of black holes out there that we just never saw because we didn't have the right type of telescope, because in human history, we only ever measured light. Light was the only way we ever knew about anything out there. And now we can see gravity effectively. And now we know, yeah, there's a whole bunch of stuff out there. There's heavy stuff, there's light stuff, there's stuff where even there shouldn't be stuff. Like, what's the difference between the biggest neutron star and the smallest black hole? There's supposed to be a mass gap, but we have found objects solidly that are heavier than the heaviest neutron star should be and lighter than the lightest black hole is supposed to be. So what is that thing? There's also a lot more mass gaps as you go up. And the biggest one is an intermediate black hole mass gap, which is like, how do galaxies exist, right? Galaxies exist because of the supermassive black hole in the middle that kind of anchors the whole galaxy into a thing. Those are like 1 million to 1 billion solar masses, right? Black holes that are kind of the mass of the sun are maybe, ordered like kind of 10 to 30-ish, 10 to 100, 10 to 50-ish solar masses. And like, is there a black hole between like 100 and 1 million solar masses? Like, nobody has ever directly observed one, and we don't know. And there's not enough time in the history of the universe for this like 1+2 thing to merge up to a million solar mass black hole. So in some sense, one of the really big open questions in astrophysics is like, how do supermassive black holes form? Like, how do they exist? And in some sense, if you don't know the answer to that, you're like, how did the first galaxies form? And what is kind of the origins of galaxies? Which is interesting because now you're like, I don't even know why galaxies exist, and we live in one. So there's all sorts of interesting open problems in astrophysics, and a lot of them are because we only look at starlight our whole lives / histories. Okay, so wrapping it up a little bit more on this topic. So gravitational waves, we saw a bunch of things in the first run, but then there was a really dramatic improvement in our sensitivity, not in the first and the second run, but in the third run. And the thing that really changed in the third run was that we started squeezing. And we'll talk about that in a few minutes. But that main point I wanted to get at there is that really improved detection rates. And then instead of in the first couple of runs, we had 11 events. We then, with another year, went up to about 90 events by improving our detector sensitivity. And that is corresponding to roughly monthly to weekly detections. And it's even more now. And so let's just spend the last little bit of time talking about how we really, really make such little measurements. And what we talk about in this context is detector sensitivity, where what sensitivity means is like, what is your signal and what is your noise? And what we want to talk about is our ratio of our signal to our noise, right? That requires that we relatively understand the signal, right? And that we make noise improvements that are targeted in our signal band. And so again, we look at these signals, there's black holes. These are different amounts of times that they go on. And there's binary neutron star mergers, and those are super different because they're so small and very zippy that they don't lose that much energy to gravitational waves, and they can go on forever in our detection band. So this is the sort of signal we're looking for. If you map those on to like, what is the amplitude of the signal in terms of that strain number, that meters compared to baseline meters, so it's dimensionless, compared to the frequency, you'll see that most black holes, if you talk about signal amplitude versus frequency of it, this is the Fourier, there's like frequency space. Yeah, most signals are kind of below a couple hundred hertz, right? That means we need to improve our noise in the couple hundred hertz band. And you can see which parts of the in-spiral correspond to which part of the noise spectrum. And then if you look at like, well, like what's the biggest noise problem across the entire band? You see that it's quantum noise, which is the noise from quantum fluctuations in the light field. That actually is the biggest limitation today for like how much of the observable universe can we see with gravitational waves? It depends on how much can we reduce quantum noise. And so quantum noise, we'll just do a quick little intro and then I'll show some photos here, but quantum noise is essentially this problem that I'm trying to measure a sine wave. That is the signal. But there are quantum fluctuations evenly distributed across the sine wave. And that just means that, again, this photon popping in and out of existence, you'll see always some minimum fuzz whenever you measure a light field due to quantum noise. And this goes back to the Heisenberg uncertainty principle, essentially the fact that a photon is a particle, even random photons that fluctuate in and out of the vacuum field are particles. Because we're measuring power, that's the number of photons per second, it's the definition of power. If it fluctuates randomly and we detect it, that's a power fluctuation. We typically call that shot noise. But then also consider that if it's randomly popping in and out, like our mirrors are on these floppy pendulums, that random fluctuation can kick our mirror. And that's the back action component of, the wave amplitude hits our mirror, we get a random kick. So there's these two parts, right? The two things that are related by the Heisenberg uncertainty principle, where and when kind of is the photon there, those show up in different ways for our detectors. And the shot noise problem is actually pretty intuitive. Probably a lot of people, maybe if you're like thinking about like engineering, you've heard of shot noise. But like the basic problem is, imagine you're trying to take a live photo at night. That's not that easy, right? Why? It's because obviously it's too dark. But why can't you just increase the exposure time if you're taking a live video of your friend walking by? You start moving, right? You're like exposed for longer, but the signal is distorted and you don't catch these fast things. So what do you really need? You need the effect of longer exposure, but with the fastness that keeps up with a moving thing. And we saw that our signals move super fast, right? These are like zippy things. We can't simply expose for longer. That doesn't work for us. And so like taking a live video at night is a classic like kind of shot noise limited thing, right? And again, just this, we won't talk about this too much, but you get randomly kicked in your mirrors. If you get randomly kicked, that is literally a position fluctuation, right? And what are we measuring? The detector literally measures position fluctuations, right? So now shot noise not only like kind of makes it, you don't get that much information. There's like these random power fluctuations, but those random power fluctuations can also exactly look like our signal. And that's the problem with measurement back action and how it shows up. And so we talk about squeezing quantum noise. Squeezing quantum noise is just about, we can't change kind of this minimum uncertainty in when and where the photon is. We can't change this half h bar over 2 from Heisenberg uncertainty, but we can shove it all into one of those. We can shove this total product into one variable or the other. We can shove all the noise into delta x, or we can shove all the noise into delta p, right? And so when we shove all the noise into delta x, we can, into delta p, we'll reduce delta x. That's what it means. It's a fixed total quantity, but you can distribute it however you like, and that's the thing. So when we do phase squeezing, we amplify the noise at the tops and the bottoms of the waves. And what that does is it implicitly de-amplifies noise in the middle of the wave. And same vice versa, right? Like if we want to reduce delta P, we can do amplitude squeezing. That is, we can blow up the noise in delta X at this middle, and that reduces the noise at the tops and the bottoms. Because it's the noise at the tops and the bottoms that kick us. It's the noise kind of in this middle that causes power fluctuations, right? So we can choose how we distribute this noise, and that's what squeezing is. How do we do that? What we have is an optical cavity, and what it amounts to is like, you see a little crystal that's held in the very middle there? That thing's about 2 millimeters by 5 millimeters by 10 centimeters, meaning it's about the size of your, like, if you have a long fingernail, it's about that size. That little crystal is in this little cavity, and like, if you look here, these screws are standardly 1 inch apart. So this is a pretty small device, really. It has this beautiful bow tie shape. We pump it in green, and then it has 1 green that converts to 2 reds, and the correlations of these two chooses what type of thing we're squeezing. Okay, for the rest of it, I'm just gonna kind of go from there and just show you photos. Yeah, I know you guys have a lot of questions about how hard is this really and what does it really look like, right, to detect stuff. And I kind of want to show you some of these photos in the next few slides just to say, like, there's a lot of different expertises involved in squeezing, in quantum noise, and in LIGO. There's all sorts of engineering, optical engineering, data science with fitting. There's really like every specialty involved. So here, this is a rough schematic. We have the squeezer, and we have what's called the filter cavity that just makes the squeezer more well matched to our detectors to reduce noise. This is like even, I would say, high level overview of their squeezing system. There's a lot of like these kind of optics tables that we deal with. We're building some up at Berkeley now. That's actually what a DT undergraduate working with me is working on. This is just a cool video because it looks cool. So when we had to upgrade the squeezer, we had to move it all. And so you can kind of see this is like a many person effort. And we have like people literally, they got their degrees in like every sort of technical field working on us on this project with us. If you look into our squeezing window, like while we're squeezing, you would see this. The thing is glowing in green because we had to pump the squeezer in green to produce the down-converted reds. We have squeezing, it goes into the interferometer through that tiny tube you see between these two big blobs. That's how we send squeezing into the interferometer. We had to build a filter cavity to just match the squeezing better to our detectors. This is the run of the filter cavity through our lab facilities. And actually, TJ is an interesting example here. He's an operator at LIGO Livingston, and he was previously one of my undergraduate students here at Berkeley in one of my classes that I taught. And so there's a lot of room for like undergraduates, graduate students, postdocs, faculty, whatever, engineers, technicians. And yeah, it's sort of cool. And the key thing that we end up with, right, is that black is our detector noise when there is no squeezing. If we don't match the squeezing to the interferometer, we get the green, right? Where we reduce the phase noise, but the green is only sending in phase squeezing. So, right, remember how if you send in phase squeezing, the amplitude noise is more? The more amplitude noise is the reason why this green is bigger than that black. That's the back action effect. We reduce one, but the other blows up. This exceeds without squeezing because it's blowing up the amplitude noise. With the filter cavity, we can match that all to the system to be amplitude squeezing here and phase squeezing here. And we can totally lower the detector noise from up here to this purple line all the way through. And if you'll remember, like most of the astrophysics we're looking for, right, is below about 200 hertz. So it's only by matching the squeezing exactly to how our detector operates that we can really do this quantum noise optimization at all the frequencies that we need to do the astrophysics. And I'll just share this cool thing, like things like what my entire research program does here is like being really detail oriented. So this crystal, turns out there's a little crack on one side of it. If you operate there, you have a lot of loss. Loss is what kills all quantum technologies. So if we recover the loss, we can actually, by moving the crystal like 2 millimeters away from the crack, we can actually recover about 10 megaparsecs of astrophysical range, which, just going back to astrophysics, is pretty far. The Milky Way is very small. It's less than 1 megaparsec to Andromeda. The local group of galaxies is like 3 megaparsecs. The local supercluster is like 30 megaparsecs. And that's, the local group is about, 50 galaxies. Local supercluster is like over 100 galaxies. Yeah, that means that in gravitational waves, by moving a single crystal by like a couple millimeters, we can see out by many galaxies in terms of astrophysical science. And so when you look at this plot again, like how many detections do we get as a function of observing time? If we don't match the squeezing, it's a huge increase compared to before. And if we do, it's an even bigger increase because we're really reducing quantum noise in the astrophysically important area. And this is kind of a big part of where the detectors are going. Like right now, we're the red curve. Again, you want the noise to go down. Noise is going down, down, down. We hope that in 10 years, we're doing even like more than 10 times better than we even are doing today. And part of that is by building 10 times bigger facilities, which is what we hope to be doing in 10 years. And again, reducing all the loss. Today, we're at like 30%. We need to be like below 10%. So these are all like these really hard technical challenges that are interesting and astrophysically going to be really cool. Because if we can actually get there in 10 years, you would be able to see the remnant from every star that has ever collapsed, potentially. That is, we could see the remnants of stars that we have never even observed electromagnetically. The first generation of stars, nobody has ever seen these so-called POP3 stars. And we could be able potentially to observe their black holes if we can look that much better. That is, if we can reduce the noise. So that's what it all kind of amounts to and ties back to in the end. Here are just a bunch of binary systems, the first 90 that we saw. You can see there's all different like big ones that move slowly, small ones that are zippy. So there's this whole catalog we're building out now. And this summer, we're going to publish the 4th one. And yeah, with better detectors, we'll see a bigger variety of events. We'll see events more often. Already, we're now at like every other day, I get a notification about events. We'll see things from smaller objects, from our multi-messenger stuff, and really like kind of be able to see further and further back in time because we are directly measuring gravity. Cool. Yeah, so LIGO scientific collaboration is really big. It's over 1,200 members, 100 institutions. I think it's now like 20 countries. And of course, this is an NSF-funded major facility, which is really important and very cool. So yeah, if you have more questions, we should definitely do them. But yeah, thanks.
We have plenty of time for questions. And also there's tons of people who have questions online.
Oh, I have no idea if we check those.
No.
There's a couple questions online.
Okay, well, would you like to share?
Yeah.
I know, like, do I start getting
Sorry, we've been ignoring them so far compared to the in-person, so we can do online.
someone
Maybe
asked,
repeat the question
Oh.
so that people can hear it.
Yeah, good idea.
yes, do gravitational waves behave like normal waves? Does it follow properties like resonance and et cetera?
Yeah. Yeah, gravitational waves are exactly like normal waves. The only difference is that they're propagated through space-time, but like what difference is that to the ocean? So yes, like you could totally imagine interference, right, from like a bunch of these like different waves. And like, sorry, just to back up for people online, the question was, do gravitational waves behave like normal waves? And the answer is yes. So you know, imagine you had a bunch of waves all going off, like imagine the ocean on a windy day. It's the same effect. That's kind of what this stochastic background would look like. If there's a bunch of waves, they all interfere and you kind of can't really tease them apart. Like, you know, it's the addition of a bunch of waves, but you're still not going to be able to nail the source unless you have a pretty good model of what it might be. Yeah.
Is there a change in mass, or would it be possible ever to like visibly see a gravitational wave, and like what would like the size scale have to be?
You could definitely, like, with so the question was, can you ever like visibly see a gravitational wave? So you can know that gravitational waves are happening. There was a Nobel Prize, I forget when, for the indirect, I think in the 80s, for the indirect detection of gravitational waves, because you can infer that they exist, because you can see a binary that collapses and know that that's the only way for binaries to lose mass. But I don't know if you can directly see it. Like, you can see the event that produced gravitational waves in the colors if that event emits light. But I guess it's like a similar question to maybe like, can you see a black hole? Like, maybe people have seen like images of like supermassive black holes that are super bright and like crazy looking. But like, what are you actually looking at there? You're looking at a black hole tearing apart the matter around it. And the matter that's getting torn apart is like glowing as its guts get ripped out, right? So that's like that's how you normally see a supermassive black hole. But is that seeing it, or is that just seeing how it destroys stuff around it? I think until the Event Horizon Telescope, you're still not directly seeing it. So I don't know that, and even that is kind of not directly seeing the gravity of a black hole, but that's seeing that it's there, if that makes sense. Yeah.
Questions in person?
Yeah.
Well, okay, I have online.
Okay.
Yeah, someone said, can we access the data of the GW and process in our computer or certain?
Yeah, I would definitely recommend going to, I forget exactly what it's called, the Gravitational Wave Open Science Center, so I know that there's like every year we have a gravitational wave open data workshop. That's a lot like the workshop that's happening here, where we kind of have like Python notebooks and all these things where you can, yeah, like all the data from the past runs is publicly available. And we have a lot of functions that are also in like libraries and packages and modules in Python where you can just like, you know, do whatever data processing, data analysis you want. We also like log a bunch of all the auxiliary witness channels in our observatory. So like if on your own you felt like doing like, you know, can I look at the coherence or the correlation between a gravitational wave signal and like a magnetometer near the photodetectors, you can do that. All of this is like publicly available stuff. Yeah, so there's a lot of resources for how to do gravitational wave data analysis and parameter estimation online.
That seems like a really great project. Remember that you have to give a presentation on something related to Python. So maybe I just like grab some of the data and making plots of it. That would be really awesome.
Yeah, if you look up GWPy, there's a lot of online resources for like getting started with the open data sets. Yeah. Yeah.
From online, if gravitational waves interfere, how can you say something about like individual sources?
Yeah, so this so something that would be like this stochastic signal, this would be like super, super small compared to something like the merger signal. So this here is completely not to scale. Yeah, like the loud signals that we see that happen once in a while, for the question that was like, asking about how can we know what we saw if they're all interfering and you have a bunch of overlapping signals. If your signal is buried in this kind of sea of unresolved interfering signals, it will be hard to impossible potentially to discern a single given one. But most of the signals we see today are not like that, right? So if you consider like this, right, you're talking about if there's this overlapping background, that would look like a blue signal that's really super small and way buried within this blue signal. but the signals we see today are still quite loud in the sense that they like this part of this chirp really clears the background noise. And so what we're looking at today are these like kind of prominent signals and not trying to pick individual ones out of this. But for like the future generation, you guys may figure out ways to like better do source identification, even within a sea of relatively unresolved things. Like this could be a big data type problem that we just don't know how to solve yet. Yeah.
How about in quantum mechanics, there's so much like uncertain principles? Why? Unlike regular science, quantum mechanics is very uncertain. Why?
That's a great question. Roll, I heard you taught upper division quantum mechanics.
Yeah,
Why?
so in quantum mechanics, it's probabilistic in nature. The idea is that, so I mean, question thing you're trying to ask is like, why does quantum mechanics work so well for describing the universe? That we don't know, right? That's just like, we don't actually have a way to prove any one theory actually describes you, right? All we have is basically theories that we make, we have a set of principles, we predict something, and then we compare it for experimentalists. And after a lot of comparison that are successful, we reach some level of exhaustion and we're like, okay, that theory holds water, right? So quantum mechanics, that said, is basically probabilistic. So the idea is that what we define is something that is called a wave function, which is telling you about the probability of finding a particle at some point in time with some properties. But you can, basically predict with you can't say definitively that particle will be there or will it be carrying some momentum. And so within that setup, what you find is that you can never say for sure where the particle is located, nor what momentum is carrying. And the limits of this uncertainty associated with its location and its momentum is correlated. The momentum and position are correlated with that constraint that we can show that delta x and delta b, that has to be greater than some number. And you can prove this. That you can derive yourself.
Yes.
So the best way to derive it is to come to Berkeley, take a class, take one of us.
Yes.
To prove this.
So
Yes.
let's say I like do physics in like high school, and I like take a class for go to college.
So I mean the normal path would be for you to take an AP physics class. So like you can take AP physics A and B, right? I think that's what it's called. Those are the standard ways, and so that would be equivalent to like the first and second semester of intro physics.
Yeah, is this AP come with quantum mechanics?
No, well, I think maybe an APB a little bit.
Like it might cover like the utility version of it, like how you use it to make an atom. Like why does the electron not collapse into the middle? How are the electron orbits fixed away? Like it might cover some of these sorts of things, like how atoms work, but it might. I think your answer, your question is a good question. Like, yeah, it won't. I don't know if there's any physics class that will tell you. I don't know if modern physics knows, like Raul was saying, like, why is the universe fundamentally probabilistic, such that quantum mechanics describes it reasonably? Like for that question, I don't think anyone knows what underlies that probabilistic nature of the universe in this sense. Yes.
My suggestion is to come to the Lawrence Hall-Sign event in July 31st and ask the panelists this question.
Yes, that would be, yes.
Sorry to interrupt. We are a little bit past our time, so students here in person whose parents are waiting for them should make their way out. Although if Vicky and Raul are free, they can of course stay and answer any more questions about the nature of the universe, but really no one has any business answering.
But before we go, why don't we thank Vicky one more time?
As a reminder, we will meet again on Friday, same time, 10 in the morning, and continue thinking about maybe stuff you want to talk about in about 2.5 weeks then for your presentation.
It's Friday or Monday?
Friday. Sorry?
Is today's Friday?
Sorry, Monday. We'll meet Monday at 10 a.m. Yes, today is Friday. Thank you guys for joining. Thank you so much, Vicky, for giving us that talk.
Thank you.
Yeah.
And take it on your way out.
Should you be scared of black holes?
Yeah.
I think you can be as scared or not scared. I used to be terrified of them, but you know, it's not really going to be a problem in your life. So in that sense, you're like theoretically scared of something that won't be a problem.
Take care. Have a good weekend.
Bye. And I feel like that eventually becomes less scary.
Yeah.
You
Wait,
can
you
be
said
scared if you want
what
to.
path should I take to like take like 1 on the 10? And if I do this, then we'll study